So sometimes it's a little hard to tell. You have to, in this case, excuse me, you have to, in this case, be able to put it into a glacial context. You have to kind of see what was happening regionally to understand that, no, this isn't just a stream. This is a stream that was associated with the glacier. And the third type is glaciolacustran. Again, glacier, and lacustrine means lake. So lacustrine sediments are lake sediments. So now I'm looking at materials that are being laid down in the bottom of lake systems. And there are going to be a lot of those around. All this water from the melting glacier, the drainage systems are still all plugged up either by sediment the glaciers dropped or ice is still plugging up the old channels. So the water is just accumulating as these big lakes along the front of the glacier. And all the fine-grained sediments, the clays, the silts, are settling out of the water, coating the bottom of the basin. And oftentimes we see them in layers like this. These are called bars. And what's cool about bars is they form in couplets, a dark and a light-colored couplet. During the summer, when the water's flowing, things are melting, the sediment's just dumping into the lake. And I get coarser material, and it tends to be much darker in color. But during the winter, hey, things freeze up, right? So but all that's happening over the lake is the fine material is settling out of the water. Ice is kind of covering it over. And as that fine material settles out, there tends to be a fair amount of calcium carbonate that also settles out. And that makes the sediment lighter in color. So I get this couplet, these two layers, a dark layer and a light layer, that represent the deposition that's occurred there for that year. So each couplet's a year's worth of deposition. So if I just count up the couplets, the light dark bands, I can tell how long it took for that sediment to accumulate in that lake basin. And notice, it gives me a rate of accumulation, doesn't it? It doesn't give me a date that it started. It doesn't give me a date where it ended. It simply says it takes this long, this many years to accumulate this thick a package, this many bars. So I can use that as a rate of accumulation, but I can't use it as an absolute age date of start and stop. But it's still, pretty handy. It can tell you a few things. Another thing that happens around glaciers, hey, this is a big pile of ice sitting out there, right? And that ice is chilling the air around it. That means there are all these little microclimates developed all around the edges of the ice. The further away you get, the warmer it is. The more into the glacier you get, the colder it is. And that means there's going to be different temperatures, there are going to be winds, there's going to be rains, mists. It's really kind of a funky weather area. But with all those winds, as things begin to dry out, all the silts, all of the really fine clays, the material that the glaciers just ground into flour, we call it glacial flour. All that material now starts getting blown around. And if you look at it, we can see this fine-grained material easily picked up by the wind. And if you look in the United States, it covers all of the Midwest and the Great Plains. This is the basis of the super great soils that we have through that area that make the Great Plains the beef basket of the world, and Illinois, Indiana, Ohio, Michigan, the corn center of the United States. It's these soils. And this material is called loess, L-O-E-S-S. If you go down the Natchez Trace, it's the oldest highway in the world, in the U.S. It parallels the east side of the Mississippi. And the way you used to get your farm produce to market in New Orleans was you built a raft, you put your produce on the raft, and you went down the Mississippi to New Orleans. You got there, you broke up the raft, you sold the lumber, you had all your products sold, and then you either bought a horse or got a carriage ride, or you walked back to your home in Ohio. And that pathway, the Natchez Trace, is worn down through the loess soils where the banks are above head level. It is just because it was powdery soil, as people walked over it, the wagons went over it, kicked up dust, it blew away, and they just entrenched portions of that pathway into these loess soils. So they're easy to see disappear. In northern China, they have loess deposits that are over 300 feet thick. Great farmland. You can see here, they haven't wasted a bit. They've terraced every bit they can. This material in China, though, didn't come from glaciers. This is the fine dust blowing out of the Gobi Desert and accumulating there as desert material. Different origin, but the same effect we have with loess. So if I look at the kind of landforms that I get from a glacier, they're really different. I get all sorts. The loess is wind-blown stuff. But as the glaciers are melting, material, glacial diamicton is just dumping out of the ice. So if it's spreading it across the area as it melts, it's this ground moraine. If the glacier stops at a spot, remember, even though it appears to be standing still, the ice is still moving forward. It's still being replenished by ice from the high back country. It's still moving down, it's still carrying debris, and as it gets to the toe or the end of the glacier, the terminus, that debris just falls out the end. It just dumps out. The only reason the glacier is just sitting there is because it's melting as fast as the new ice and debris is coming in. Now it starts melting faster, and the ice starts pulling back. It melts back faster, and it gets replenished. But when it's just sitting there, just dumping out debris at its terminus, we end up with what's called a moraine. And in this case, we're calling it a terminal moraine because it's as far as the glacier got. It's the terminus, end of the line. But what if the ice melts back a ways and then it stops again? Well, then we call it a recessional moraine because it's receding, and it was kind of a temporary stop during that recession. So you can have a whole bunch of these recessional moraines. Sometimes that happens, and then all of a sudden, whoa, we got a lot more ice coming down. It's been a couple of cold years, and now the glacier starts advancing again. And it overrides these moraines, spreads them out, moves up, and builds another moraine, another terminal moraine. Well, it may have only got, say, to here. So that's where its terminal moraine is going to be for the second advance. So I've got a terminal moraine from the first advance, a terminal moraine from the second advance. And how do I know that second terminal moraine isn't a recessional moraine from the first time when it was retreating? Pretty hard to tell. You have to kind of look at what was happening regionally to try and see if there was a re-advance or not. This is where it gets tricky, picking all this stuff apart. And oftentimes, you can't really tell too well. So, interesting. Okay, around here we've got a lot of lakes. And these are what we call kettle lakes. The ice is retreating, but the ice is just kind of melting. It's getting really funky, punky, kind of rotten looking. It looks kind of spongy. And it's just sitting there melting in place. It's really kind of become disconnected from the glacier itself. It's just a big mass of ice just sitting there. The glacier's back there melting away. Sediment's being dumped out. Water's carrying this material out as outwash, laying down sheets of sorted sediments up in front of the ice. And as it does that, it starts to bury this unmelted chunk of glacier that's just sitting out there. Well, that means there's no deposition going on in that spot. Eventually the ice melts. But because there was no deposition there, when the ice melts, it leaves a hole. And if that hole's deep enough that it intersects the water table, it's a hole full of water. if it doesn't intersect the water table, it's just a hole. Water table is still below it. So if it's just a hole, we call it a kettle. If it intersects the water table and it's full of water, we call it a kettle lake. But wherever you see one of these kettle lakes, you know that was a spot where some of this rotten ice, last to melt, gotten buried, and prevented any sedimentation from occurring. If you go down Oakland and you go to Wood Lake, just down there by the D&W down the street, that's a glacial lake. It's a kettle lake. All of the lakes around here are like this. Another thing I can have happen is there's a hole in the ice. And as debris just falls out of the ice into that hole, well, it forms a big stack of debris, and then as the ice around it melts away, I've got a mountain of this glacial debris just sitting on the till plane, and we call that a cave. Or if it comes out of the ice and it just kind of fills in the space between the side of the valley wall and the ice, and it leaves a cane terrace along the side. So there are all sorts of landforms that I end up getting that are kind of unique. Let's take a look at a couple of these moraine systems. Here we're back looking at a valley glacier. Erosion's going on, right? So it's kind of back to our other kind. But look what's going on here. You can just see there's a valley glacier. There's one. There's the cirque. There's the valley glacier coming out. Another cirque valley glacier. And they're all coming down and merging in this one big central valley. But look how along the walls, the ice is chewing up the valley walls. That debris is being carried along. And if it's along the edge of the valley, we call it a lateral moraine. When the ice leaves, that debris is still going to be there. And we call it a lateral moraine because it was on the edges of the ice. But look what's happening here. Here we have the lateral moraine of this glacier and the lateral moraine from this glacier. You notice how they meet. And once they get past that point where they join, now that moraine isn't at the sides, but it's incorporated within the glacial ice as it flows down the big valley. Now we call it a medial moraine because it's in the middle. And you can see this glacier has 1, 2, 3, 4, 5, 6, 7, 8, 9 medial moraines in it. Each one of them representing a past lateral moraine is merged with another lateral moraine. So that means it's had 9 sources of input, 9 different cirques feeding into this glacier at this point. So you can just see how this is occurring. Our lateral moraines merging to form medial moraine. Okay, the ice gets to the bottom of the hill. It spreads out. It gets to where it's going to go. You can see the glacier here. Look at the medial moraines that it left on each side. The glacier ice is obviously in retreat now. So we're seeing the medial moraines, and here we're seeing the terminal moraine. This glacier ice didn't get much further than the end of the valley. But if we look across Michigan, wow, we can see these moraine systems all over the place. And it's really pretty cool. Here we are. Here we are in Michigan. Here's Saginaw. Here we are right in Kalamazoo, Lake Michigan, Huron, Erie here. And you can just see how the ice flowed down through these troughs, these Great Lakes troughs. And you can see the terminal and recessional moraine systems that they left. So here you've got Lake Erie ice low. Here you've got Lake Michigan ice low, Saginaw ice low. Look how complex it gets kind of in here, where these lobes all kind of merge and cross-cut each other and fight for territory back and forth. It gets pretty crazy trying to figure it all out. And it isn't just Michigan. You can see these ice lobes extend all the way down into Indiana, Illinois, Ohio, other lobes further west, down into the Dakotas, Montana, and you look at these ice lobe systems, you just kind of see how these lobes came in, and even the shape of the state now is somewhat carved out, in the shape of the Great Lakes is carved out by these glacial lines and funneled along these trough systems. So remember I talked about river systems, and we said the Mississippi drains just a whole big chunk of the U.S. And remember when I said, wasn't it kind of weird that it drains all the way up here right to the southern border of Lake Michigan, and that water goes all the way down the Mississippi to enter the Gulf of Mexico, hundreds of miles away. Why doesn't that water just drain to Lake Michigan? It's so much shorter. You'd think it'd be a lot easier, wouldn't you? But it doesn't. Well, it doesn't because the glaciers have left moraine systems that have basically blocked all those drainages. And now the drainage can't go northward. Its only option is to go south. If you look at the shape of the Ohio River right here, and the shape of the Missouri River right in here, they follow those courses because that's where meltwater from the last glacier, or two or three, was moving along the edge of the glacier. That's the only way it could escape, was to travel along the edge of the glacier. And it carved out a new channel where that glacial ice sat. And now that's become the preferred channel for the Ohio and the Missouri rivers. So those two river patterns, for the most part, represent ice age positions, ice positions during the retreat of the last Wisconsin ice sheet. So it really has a dramatic effect on the drainage pattern and the development of the topography that we enjoy today. True or false? Moraines result from deposition along ice margins and often give clues as to how a glacier advanced and retreated. 1 second. Okay. Everybody says true. Yeah. Wow. Pretty obvious, isn't it? I mean, you can just see the terminal conditions down here in this last ice advance, and you can see how the recession layers just retreated and everything just kind of moved back up through the valley systems that it was carving. Beautiful example. And down here, you can see the same thing from a previous glacial event that went even further. And now it's been overridden by the latest event, so that's pretty much obliterated previous event in those areas. Okay, here's some Kettle topography. Remember we talked about Kettle Lakes. This is over in Wisconsin, kind of halfway between Madison and Milwaukee as you come across on I-94. And this is part of the Kettle Moraines State Park area. And you can see these were areas of stagnant ice. The ice prevented the outwash from building up and depositing. And then when ice finally did melt, there's the water table right there at lake level, right? You even see this out on Cape Cod. You know how Cape Cod kind of goes out into the Atlantic and then kind of looks like a fish hook as it goes northward? Well, that spine, that northern spine, is actually a moraine system between two ice loads. And then on top of that, all the sand got deposited as the ice melted. And again, a whole series of Kettle Lakes formed in that terrain. So you've got all these Kettle Lakes through the middle of the Cape Cod area. Remember when I said we could, fill up a hole in the ice with debris and it would leave a cane, leave a little mountain of debris? Well, here I've got a topography setting where I've got Kettle Lakes and I've got canes all mixed together. Both things are going on, so it really gets to be pretty wild and crazy. Okay, y'all remember Roche-Moutonnez, right? What does